In ionic compounds, one atom or group of atoms gives up one or more electrons to another atom or group of atoms. The resulting cations and anions are held together by electrostatic attraction between positive and negative charges. An important thing to remember is that ionic compounds are overall electrically neutral. The total positive charge of all cations is the same as the total negative charge of all anions. Therefore, for compounds that are formed by cations and anions with predictable charges, the chemical formula of the compound can be deduced based on these charges. Consider the example of sodium chloride. Sodium is an alkali metal, and when it forms an ion, always donates its only valence electron, so the charge of the resulting cation is always plus. Chlorine is a halogen, and when it forms an ion, always accepts one extra electron, so the charge of the resulting anion is always minus. Because each sodium atom in sodium chloride donates one electron, and each chlorine atom accepts one electron, in order for the compound to overall be electrically neutral, the number of sodium cations and chlorine anions in it must be the same. In other words, the ratio between the number of sodium cations and chlorine anions is 1:1, and the empirical formula of the compound is NaCl. Similar reasoning may be applied to magnesium oxide, a compound that is composed of magnesium and oxygen atoms. Magnesium is an alkaline earth metal, and when it forms an ion, always donates both of its valence electrons, so the charge of the resulting cation is always 2+. Oxygen is a nonmetal in group 16, and when it forms an ion, it always accepts 2 extra electrons, so the charge of the resulting anion is always 2-. Because each magnesium atom in magnesium oxide donates 2 electrons and each oxygen atom accepts 2 electrons, in order for the compound to overall be electrically neutral, the number of magnesium cations and oxygen anions in it must be the same. In other words, the ratio between the number of magnesium cations and oxygen anions is 1:1, and the empirical formula of the compound is MgO. Now consider aluminum oxide, a compound that consists of aluminum and oxygen atoms. When aluminum forms an ion, it always donates its 3 valence electrons so the charge of the resulting cation is always 3+. We already said that when oxygen forms an ion, it always accepts 2 extra electrons, so the charge of the resulting anion is 2-. So one aluminum atom donates 1.5 times more electrons than one oxygen atom can accept. Therefore, the number of oxygen atoms in aluminum oxide must be 1.5 times greater than the number of aluminum cations. The smallest whole number ratio that is equal to 1.5 is 3:2, so there must be 3 oxygen atoms to every 2 aluminum atoms. Therefore, the empirical formula for aluminum oxide is L2O3. Then the 2 aluminum atoms will donate 3 electrons each for a total of 6 electrons, and in turn, the 3 oxygen atoms will accept 2 electrons each for a total of 6 electrons as well. Oxygen atoms will accept all electrons donated by the aluminum atoms, so the compound will overall be electrically neutral. Notice that the number of cations in the smallest unit of aluminum oxide, 2, multiplied by the magnitude of the charge of one cation, 3 times the magnitude of the charge of an electron, is the same as the number of anions in the smallest unit of aluminum oxide, 3, multiplied by the magnitude of the charge of one anion, 2 times the magnitude of the charge of an electron. This condition holds for all ionic compounds, so it can be a useful check to see whether the empirical formula of a compound is written correctly. Metals that form different types of cations, such as iron, a transition metal, can often form more than one ionic compound with the same nonmetal or halogen. For instance, iron commonly forms 2 different compounds with oxygen. In one of them, each iron atom donates 2 of its valence electrons, forming the iron 2+ cation. And in the other, the iron atom donates 3 of its valence electrons, forming the iron 3+ cation. In both cases, each oxygen atom can only accept 2 electrons, forming the O2- anion. Therefore, the empirical formula for these 2 compounds of iron with oxygen will be different. For the first compound, each iron cation has charge 2+, and each oxygen anion has charge 2-. So in order for the compound to be electrically neutral, there must be 1 oxygen anion per iron cation. The empirical formula for this compound is then iron O. For the second compound, each iron cation has charge 3+, and each oxygen anion still has charge 2-. So in order for the compound to be electrically neutral, there must be 1.5 times as many oxygen anions as there are iron cations. The smallest whole number ratio between the number of oxygen anions and the number of iron cations in this case is 3 to 2, and the empirical formula for this compound is then iron 2O3. In some cases, the anion, or less often the cation, in an ionic compound is not a single atom, but rather what we call a polyatomic ion, also known as a molecular ion. Polyatomic ions typically consist of 2 or more nonmetal atoms connected by covalent bonds. The polyatomic ion as a whole, rather than individual atoms that form it, donates or accepts electrons and becomes electrically charged. We said in the lab that when ionic compounds are dissolved, the cations and anions separate from each other and drift in solution independently, a process known as dissociation. This is in contrast to molecular compounds, where all atoms that form a molecule remain together even when the compound is dissolved.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
When an ionic compound that consists of a polyatomic ion and another ion is dissolved, the polyatomic ions dissociate from the other ions in the compound. However, the atoms that form the polyatomic ion do not dissociate from each other because they are connected by covalent bonds just like atoms and molecules. Instead, the polyatomic ion drifts in solution as a whole. We will talk about why and how polyatomic ions are formed a bit later in the course. For now, please remember the chemical formula, names, and charges for the following common polyatomic anions. Acetate, C2H3O2 minus. Carbonate, CO3 2 minus. Cyanide, Cn minus. Chloride, ClO2 minus. Chlorate, ClO3 minus. Hydroxide, OH minus. Nitrite, NO2 minus. Nitrate, NO3 minus. Phosphide, PO3 3 minus. Phosphate, PO4 3 minus. Sulfide, SO3 2 minus. And sulfate, SO4 2 minus. The superscript indicates the total charge of the polyatomic anion, not a charge of an individual atom in it. This list of polyatomic anions is far from complete, but the anions included in it are some of the most common and the only ones that we will deal with in this course. There are also a number of polyatomic cations, although they are less common than polyatomic anions. The only polyatomic cation that you need to remember is ammonium, NH4+. When writing the empirical formula of a compound that contains a polyatomic ion, the requirement that the compound as a whole must be electrically neutral still holds. Consider the example of a compound that consists of calcium cations and nitrate anions. Calcium is an alkaline earth metal, and when it forms an ion, always donates both of its valence electrons, so the charge of the resulting cation is always 2+. The charge of a nitrate anion, NO3-, is minus. Therefore, in order for the compound to be overall electrically neutral, it must contain 2 nitrate anions per calcium 2+ cation. In other words, the ratio of the number of nitrate anions to the number of calcium 2+ cations is 2:1, and the empirical formula is calcium in parentheses NO3 2. We put the nitrate anion in parentheses to indicate that the subscript 2 applies to the anion as a whole, not to individual atoms. Saying that this compound consists of 1 calcium 2+ cation and 2 nitrate anions implies that it contains a total of 2 nitrogen atoms and 6 oxygen atoms, because each nitrate anion contains 1 nitrogen atom and 3 oxygen atoms, and there are 2 nitrate anions. Some compounds may consist of 2 polyatomic anions. An example of such a compound is ammonium hydroxide that consists of ammonium cations, NH4+, and hydroxide anions, OH-. Because the charge of an ammonium cation is plus, and the charge of a hydroxide anion is minus, there must be equal numbers of ammonium cations and hydroxide anions in the compound in order for it to be overall electrically neutral. Therefore, its empirical formula can be written as NH4OH. Notice that even though hydrogen is present in both the ammonium cation and the hydroxide anion, we do not add the numbers of hydrogen atoms in them together and write the compound formula as H5NO, although that gives the correct numbers of atoms for all elements. Rather, it is customary in chemistry to keep atoms that form a polyatomic ion together, hence the form of the formula NH4OH.